Curves. They're everywhere. In the logos we see every day, in ancient architecture that stood for centuries, in the solar system, in how basketball soared towards the hoop, and yes, even in pop culture. Today, we're talking about three of the most iconic curves in math: circles, ellipses, and parabolas. These shapes aren't just in textbooks. They're hidden in plain sight, so buckle up as we explore what they are, how their formulas work the way they do, and how they shape the world around us. Let's start with circles. Since the beginning of time, people have noticed circles. Look at the sun, the moon, ripples in water, but nobody really knew what it ever meant. That was until around 300 BCE, when an ancient Greek mathematician named Euclid clearly defined what a circle was in his mathematical treatise titled Elements. In Elements, he defined a circle as a shape where every point that lie on the shape was an equal distance from the center. That idea that every point that lies on the edge was equidistant from the middle is the foundation for everything we know about circles today. Speaking of which, let's get a current opinion about circles. Italian, what do you think about circles?
What do I think about circles? Well, they're pointless.
Now, how do we turn that all into an equation? Well, it all boils down to the distance formula, which we mentioned earlier when we said that every point that lies on the circle is an equal distance from the middle. The standard distance formula between 2 points, x and y, and h and k, is given by this. For a circle, every point that lies on the edge is exactly r units, the radius, away from the middle, h and k. So, we set the distance formula using the center h and k equal to r. But, to make things easier, we square both sides. That's the standard equation of a circle. It simply states the distance between any point on the circle, x and y, from the center, h and k, is always r. That's Euclid's theorem written out in algebra. Now, let's try this with an example problem, where we try to find the center, h and k, and the radius. First, let's put our example problem right next to the formula that we know, which easily gives us our center, h and k, and our radius squared. When you look at them side to side, you can easily locate the h, which in this case would be 2, the k, which in this case would be -3, and the radius squared, which in this case would be 16, which means that the radius is 4. There you have it. It's easy as that. The center for this problem is 2 and -3, and the radius is 4.
Aha! The ellipse. A shape of exquisite mathematical beauty. Unlike its humble cousin, the circle, the ellipse has depth, intrigue, mystery. It's not just a stretched out circle. It is the backbone of acoustics, planetary motion, and even architecture. Now imagine taking two thumbtacks, looping a string around them, and pulling it tight with a pencil. What shape would you have now? Not a circle, no, but an ellipse. A special little shape, dictated by two very special little points, the foci. These little mathematical marvels dictate the shape of the entire ellipse.
And that, dear scholar, is only the beginning.
The equation of an ellipse depends on its orientation. Here is the equation for an ellipse, and here is what that ellipse might look like. However, if we were to swap the A and the B, this is what the ellipse might look like. As you can see, it went from being horizontal to being vertical. And in this formula, the H and the K is the center of the ellipse, the A is the semi-major axis, and the B is the semi-minor axis. Every ellipse has two axes. The first is the major axis, which is the longest. It stretches across the widest part of the ellipse, and its total length is 2a. That means that half of the major axis, the semi-major axis, is equal to A. The other axis on the ellipse is the minor axis, which is the shortest. It is perpendicular to the major axis, and its total length is 2b, which means that the semi-minor axis is equal to b. If you wanted to turn this ellipse into a vertical ellipse, all you have to do is take the A and the B and swap them so that the major axis lies under the y in the denominator and the minor axis lies under the x in the denominator. Remember the thumbtacks from earlier? Those are the foci. The foci are two special points located inside the ellipse. Every point that lies on the ellipse is the same total distance from the foci. The foci are located at a distance c from the center of the ellipse, where c squared equals a squared minus b squared. So, how do we measure how stretched out an ellipse is? That's where eccentricity comes in. Eccentricity is given by eccentricity equals c divided by a, where c is the focus and a is the semi-major axis. If e equals 0, it is a perfect circle, and the closer e gets to 1, the more stretched out the ellipse is. An ellipse also has a directrix, which is a fixed reference line. It is tied to the foci and eccentricity and helps define the ellipse's shape mathematically. The equation for it for a horizontal ellipse is x equals a squared over c, and for a vertical ellipse, it's y equals a squared over c. It's just another way of explaining how stretched an ellipse is. Now, let's look at an example ellipse centered at 0, 0. First, we have to determine the ellipse's orientation, which we mentioned earlier. If the bigger denominator falls under the x-axis, it's going to be horizontal, which in this case it does. Now that we know that, we can find the semi-major axis, the semi-minor axis, and the foci. The equation that we know gives us the semi-major axis squared, which is a squared. So, in our equation, to find the semi-major axis, we just have to take the square root of the bigger denominator. In this case, that's 36, meaning the semi-major axis is equal to 6. To find the semi-minor axis, we do the exact same thing, taking the square root of the smaller denominator, which in this case is 16, meaning our semi-minor axis is equal to 4. Now, to find the foci, we look at our equation from earlier, which states that c squared, the foci, is equal to a squared minus b squared. So, we can set that equal to c squared equals 36 minus 16, which means c squared equals 20, and c equals root 20. So, our foci are located at root 20 on both sides of the x-axis. To find how stretched out this ellipse is, or the eccentricity, we can also look at an old equation from earlier, which states that eccentricity is equal to the focus, c, divided by the semi-major axis, a. In this case, that is root 20 divided by 6, which gives us a number around 0.75. Because the eccentricity is greater than 0 but less than 1, we can confirm that this shape is an ellipse. We can do the exact same thing for the directrix. Because we know that this is a horizontal ellipse, the directrix is going to be x equals a squared divided by c, which means the directrix is 36 divided by root 20, which gives us a number around 8.06.
I got the suspect. It's over! We know what you've been working with. You know nothing! Know what you did. Now we can do this the easy way, or we can do this the hard way.
I'd love to see the hard way.
Let's start simple. You were caught red-handed messing with the parabola, and we want to know everything. The focus, the directrix. Where are they?
Beats me, dude. It could be anywhere. Parabolas, mysterious things.
Listen, punk. We're not leaving this room until we know the truth. You want to make this difficult? We have ways of making people talk.
You know nothing. You don't even know how to find the focus, do you?
You want to play games? Let's see if you like this.
Fine, okay. I'll talk. The focus. It's always 1/4A away from the vertex.
Go on.
And the directrix? It's the same distance, but in the opposite direction. Y equals negative 1/4A.
See? That wasn't so hard, was it now?
A parabola is the set of all points that are equidistant from a fixed point, called the focus, and a fixed line, called the directrix. Here is the standard equation, or vertex form, of a parabola, where h and k are the vertex, or the turning point of the parabola. A is how wide or narrow the parabola is, or the stretchiness factor, and a positive A means that the parabola opens upwards, and a negative A means the parabola opens downwards. Finding the focus and directrix of a parabola is really easy. If the parabola is opening upwards or downwards, the x value of the focus is the same exact x value as the vertex. The y value of the focus is the y value of the vertex plus 1 divided by 4 times A, or A being the measure of how wide or narrow the parabola is. Then, to find the directrix, you just do the negative of that. So it'll be, and instead of it being y plus 1 divided by 4a, it's y minus 1 divided by 4a. Now let's look at the sample equation in vertex form and try to find the vertex, the focus, and the directrix. First, let's see whether or not the parabola is opening upwards or downwards. To do that, let's see if our a value is positive or negative. In this case, it is a positive 2, meaning the parabola opens upwards. Now let's look for our vertex. When we put it next to the equation we know for the vertex form of a parabola, we can easily just locate h and k. But in this case, it's 3 and 1, meaning that the turning point to open upwards for this parabola is at 3 and 1. Next, because we know this parabola opens upwards, the x value of the focus is the same exact x value as the vertex, or 3. The y value of the focus is the y value of the vertex plus 1 over 4 times the a of this equation. So that's 1 over 4 times 2, which equals 1 over 8. So the focus is at 3 and 1 plus 1/8. Now, the directrix is the same exact thing, except the y value is at 1 minus 1/8.
I'm still here whispering your name. Guess the heat drives people crazy. Slip up and I call you baby. The summer's over. Guess you won't be coming over. Good to meet you, nice to know you, nice to know you, nice to know you, nice to. Isn't it strange how the shade can burn? How you can go to school but you can never